Today we're going to talk, or it's the first technical discussion of the actual solar cell device itself. We talked last class about the sun and about the nature of the solar resource. Today we're going to be talking about the interaction of light with matter. In particular, we're focusing on light absorption. This lecture could alternatively be called light not getting absorbed or optical losses. Both are important and both are related, as we'll see. So this is part of the fundamentals of the course. Just to situate ourselves, we're here right now in the fundamentals, the first third of the course. Then we'll talk about the technologies and the cross-cutting themes. And what we're going to talk about is extremely important because it allows us to understand the technologies once we begin discussing them and we discuss cost trade-offs of implementing this particular technique to the wafer to absorb more light. We can appreciate how much, we can quantify the impact of that technology development, and we can also later on ascribe a cost to it to determine the total cost-benefit analysis. So convergent efficiency is really what dictates the performance of the device, the solar cell device. It's how the solar cell device converts sunlight, the input energy, to some usable output energy, which is in the form of electricity, typically from a solar panel. So the electricity coming out of these leads, for instance, right here. And that conversion efficiency, that simple equation, for most solar cells can break down into the following. You have inputs. Sorry for the small font here. This reads solar spectrum. That's your input. Your output, which is the charge collection. It's a collected charge coming out of your device. And a bunch of steps in between. So from the solar spectrum, we have to absorb that light. Then we have to excite charge within the material. Then that charge has to move around inside of the material to get to the metallic contacts on the front side. Charge separation has to occur for there to be a voltage. And finally, the charge collection process. And so the total efficiency of this device is the product of each of these individual processes. And so if you're making a solar cell device, and I know about a third of you are, based on your background surveys, this diagram right here will ring true to you. It's Liebig's law of the minimum. What this is representing is a barrel that has water being dripped into it, and the water will flow out of whatever piece of wood is the shortest. And in the case of a solar cell device, you can ascribe a certain name to each of these pieces of wood. We'll learn what each of those are with time. But one of the big ones is optical losses. And the optical losses tend to be rather severe on some of our lab scale cells. So one of the easiest ways of boosting efficiency is simply to take care of your optical losses and to minimize